Hello there. Let's take a look at another application of the timer module. We know we can light up LEDs by connecting to a GPIO pin in the EKRA6M4. But can we also control the brightness of these LEDs? Well, one of the techniques to control the brightness of the LEDs is to use the pulse width modulation feature of the timer module. In this mode, the width or duty cycle of the voltage supply is varied for a high frequency of pulses. Effectively, what this does is to create a perception of relative brightness of the LED. When we supply close to 100% duty cycle, we see a bright light. As we decrease the duty cycle, we can see the light getting dimmed. In this exercise, we are going to see how to configure such functionality in E-Squared Studio. For this demo, we are going to make use of a built-in LED on the EK board, which is connected to pin 400. What we are going to do is configure the output of this pin in such a way that the voltage supplied to the LED creates a dimming effect. The general program flow looks something like this. We need to open the timer, start the timer, and get information of the current timer. Based on this info, we shall calculate the duty cycle factors. We shall then set a duty cycle of our choice. And then we shall repeat the process of setting a new duty cycle in a loop. Let's open a new project in E-Squared Studio. We are going to name it PWM1. We will select the latest FSP version present with this IDE, which is 5.4. And then, as the board, we are going to select the EKRA6M4. By keeping rest of the settings in normal mode, we are going to make a bare metal minimal project. When the project is loaded, we shall open the project configuration to view. Then we will navigate to the Stacks tab and look for a timer stack. Timer General PWM or R_GPT is the stack that we need for this application. When we click on the stack, we can see the properties of this stack. It is here we need to make the configuration changes. If you hover on the options, you will see a detailed description of that setting. Our first configuration change is to enable the pin output support. Then we will check the general settings. The name G_timer0 sounds about right, so we shall keep it. Next, we will make the channel for the timer to be 6. Channel 6 is connected to the pin that supplies power to the LED. There are several modes this timer module can operate on, such as the periodic mode, which generates a square pulse, or periodic interrupts, one-shot interrupts, saw wave PWMs, and triangular wave PWMs. Each of these enable certain additional configuration options. For our application, we shall select the saw wave PWM mode. For the period, we will keep it at 10,000 and with the unit of raw counts. Next, we shall configure the output of this timer. We have a default duty cycle here which is set to 50. It can be changed later within the application. The output pin is labeled as GTIOCA and needs to be enabled. We can use 2 pins from this single timer module, but for this demo we shall just use 1. That's the configuration that needs to be changed for the pin. Next, we need to ensure that the actual pin number has been assigned to this GTIOCA pin. Since we are using channel 6, the pin is called GTIO6A. And we can see no pin has been assigned to this. We navigate to the Pins tab. We know that we need to utilize pin P400, which is connected to the red LED, default named LED 3. Now, this pin is currently set as a GPIO pin. What we need is to configure it as a timer output pin, so we disable it first. Then, we move on to the timer's configuration. We can see that the channel 6 is already enabled. Looking inside, we will find that the 6A pin has no assignment. So, we will click on it and see the pins that may be utilized by this channel. There are a few pins including P400, which is the pin we need. Now, if we were to connect an external LED, then we may have used the other pins here. We select the P400 and move to the Stacks tab. As we expand the timer stack and view its properties, we will see that now a pin has been assigned to the channel 6A for the general timer. Next, if we view the Developer's Assistance menu, we will see that there are HAL APIs for the I/O port, but nothing yet for the timers. So, we click on Generate Project Contents to generate the APIs for this timer, which is configured with the parameters we have just chosen. And you can see that a set of new APIs have appeared in the Developer's Assistance. Now, we can move to the coding part for this project. We will open the HAL entry file from the source folder. To start, we will declare two global variables of integer type, PWM period and white cycles. And then we can proceed to the HAL entry function. Again, we will declare a variable info with the data type timer info t, which is a proprietary FSP data type, and an FSP error status variable or initializing it to FSP success. On the third line, we will pull in the API for opening the timer module, followed by an assert macro to ensure the previous API has been executed successfully. We shall start the timer module with the GPT start API. This is also followed by the assert macro. Then we will make a while loop. In the while loop, we will try to adjust 3 brightness levels of the LED by utilizing the PWM method. First, let's set the LED to high brightness. Step 1 is to get the timer info. We can use the info get API for that. And we shall use a pointer to the info variable that we had created previously as an argument to this function. After inserting the assert macro, we shall store the value from the period underscore counts member of info variable to the PWM underscore period variable. This PWM variable will be used as a basis to calculate the duty cycle of the timer PWM signal. Next, we shall perform a calculation and hold the result in white cycles. Basically, we are going to multiply the PWM period value with the duty cycle. In this case, it is 80, and then divide by 1000. Once we have that value, we are going to use it in the duty cycle set API, which sets the duty cycle value for this timer operating in PWM mode. The API also requires naming the timer pin, since this timer module can operate 2 pins. For our case, it is going to be the A pin, so we shall write GPT underscore IO underscore pin underscore GTIOCA. And the duty cycle set API will be followed by the assert macro and a small delay. This delay is the duration during which the LED will be lit at this particular brightness. We will then write the code block for medium and low brightness. It is essentially going to be the same as before, only the value of duty cycle need to be changed. So we will copy the entire code block. Once we have pasted the code block, we will change the value of 80 to 40, which will create a smaller pulse width, thereby reducing the brightness of the LED. We shall then paste the code block for low brightness setting. As with the previous, we will change the value to 10, so white cycles value is further reduced. This should roughly be the code we need to light the LED consistently with varying brightness. So let's go and build the program. We build the project first and see if any errors appear. As no errors have been found, we can proceed to debugging mode and upload the program onto our board. Once the program has uploaded, we can press this resume button twice to run the program on the board. And we will see that the LED 3 is being lit up and the brightness is being changed periodically to 3 different levels. This is the result of setting 3 duty cycles for the supply voltage that is being provided to this LED utilizing the timer module in PWM mode. So yes, that's how you can change the brightness of an LED or even sound of a piezo buzzer using the pulse width modulation feature of the timer modules. See you in the next video.